This is part two of the Neurips discussion. I attended Neurips 2023 in New Orleans. And the second part is focusing on four papers that were presented. I'm going to talk about a paper that was presented by NVIDIA and others using large language models for traffic scenario planning. Another paper, also NVIDIA and others, where large language models are used for reward function design in robotics. Then a paper about direct preference optimization, which is the idea that you can use existing data sets, kind of like offline reinforcement learning, and then deduct from the prioritization function that you, deduct the prioritization function from that data and apply it directly in fine-tuning a large language model. So basically you can circumvent reinforcement learning with human feedback. And lastly, related to that, OpenAssistant, which is an open source data set that is gathering thousands of conversations between LLMs and humans. And the idea of the data set is to find exactly the kind of data set where, let's say, you align human preferences with the output of LLMs. This is not even wrong podcast. It's December 20th, 2023. This is Delco. Today the fund is down 9.5%. The market's down 1.5%. For the year, we are up 115.7%. The market's up 22.7%. We're outperforming by 93%. Just real quick about the market. I could not find any specific reason why the market sold off. It did sell off towards the end of the day. Tesla has been underperforming throughout the day, and I will discuss later on if there's any information about what happened today to the market. But my suggestion is probably it could be a Fed official saying something about interest rates. Clearly, interest rates are driving the short-term trajectory of the market. Now let's talk about Neurips part two. Like I said, I'm going to start with a paper by NVIDIA and others. The name is a little bit unlucky, I would say, Trajenglish, learning the large language of driving scenarios. So the name, you can argue, is maybe not as creative as it should be, but the idea is really interesting. And the idea is that you tokenize a traffic scenario, and then you use transformer architecture to generate the maximum likelihood estimation of the next possible traffic scenario, and you go from there. Tesla has actually shown that in their AI Day in 2022 that they do things like that. So this is already being used in production. NVIDIA actually spoke with the authors. NVIDIA is doing this also with the idea of going in production, in particular with Mercedes-Benz. Now, the actual intricacies of the model, like everything else, the devil's in the detail here. Once you read the paper, you realize how involved these types of works are. It sounds pretty simple. You just tokenize a traffic scenario, and then you do maximum likelihood estimation. But it really goes pretty far, right? You have to. So here are some highlights from the paper. The idea is to tokenize traffic scene, use transformer architecture to predict the next state of all actors. A simple data-driven method for tokenizing trajectory data we call KDisks that enables us to tokenize the Waymo open data set at an expected discretization error of 1 centimeter using a small vocabulary size of 384. What that means is that they're using, that they have the way they tokenize this traffic scenario is by coordinates. They have a bit of an error, I guess 1 centimeter. You can be off by 1 centimeter, which is probably rough, much bigger than you might think, because the traffic scenario is not real world. But anyway, and then the vocabulary is 384, so we have 384 tokens here. That's obviously incredibly small. A transformer-based architecture for modeling sequences of motion tokens that conditions on map information and one or more initial states per agent. Our model outputs a distribution over actions for agents on a time, one at a time, which we show is ideal for interactive application. state-of-the-art quantitative and qualitative results when sampling rollouts given real-world initializations, both when the traffic model controls all agents in the scene, as well as when the model must interact with agents outside its control. So what they're saying is, first they're giving you, like I said, some indications of how precise the model is and what the vocabulary size is. What's more important, I think, is that the second part is form-based architecture, and they have certain, they do certain what's called ablation studies. So they look at the model and they say, what if we control, what if every agent is subject to the model? And then what if we control certain agents and then just have certain other agents being subject to the model? So I find that that's obviously very important for further extrapolations of the model. For example, if you look at a scenario where you are a self-driving car, so you have all these other agents doing stuff and you only control your own action, you obviously will have a little bit of a different model. Okay. Questions that I have for this is, of course, well, how is this better than behavioral cloning? Obviously, it's better than behavioral cloning. It's an additional estimation, it's additional input, it's additional information that can be used. What is the computer memory budget? People have discussed the Tesla approach, and it's fair to say that Tesla's hardware has not been optimized for transformer architecture. So therefore, the question is, how can they circumvent that? My personal favorite, how can symmetries and variances and things along those lines be used to increase the efficiency of compute? But what I mean with that is, for example, you have things in traffic, right? Let's say if a car is all the way to the left of a lane, he's not gonna go even further left, right? If a car is in the middle of a crossing, he's not gonna go backwards. If a car is in a one-way street, you can assume he's just gonna go one way. So there's certain things you can, you have these symmetries or asymmetries, if you will, but you have information in the set of the traffic scene that will lower the compute budget. So overall, I think really interesting work. If you think about it more generally, actually, what I wanted to add here is that people, and in the paper they discussed this, people have been using attention, diffusion, CNN, RNN, DPO, like a lot of, well, DPO is a little bit outside of the scope here, but my point is the following. You have a lot of models that are trying all to do the same thing, which is really do a maximum likelihood estimation. So I have an input, I have a certain variable that goes in, and now I'm trying to guess what is the distribution that this variable belongs to. In other words, what's the next time step scenario? What's most likely the scenario of the next time step? This is what diffusion's doing, what transform's doing, CNN and RNNs in this recent work that I discussed yesterday. Actually, Chris Rhee in his lecture spoke about this. So we can use linear models, we can use filters. The problem is always the same, right? We have an input, and we want to understand how the function, or what kind of function can we construct that takes that input and learns from many examples, creates a function, and then outputs something that we can use. Next is a model, a paper, excuse me, based on the model that I've discussed before. It's Eureka, human level reward design via coding large language models. So this goes into a direction that I'm very, very excited about, which is function design, program design. So you can use large language models to sort of bootstrap themselves towards a solution. This is the idea. In this case, what they're doing is design reward functions. And the idea is that you have, you're given a certain task, And now you have to figure out a way to teach the robot how to do that. Reinforcement learning is often used in robotics, but the problem with reinforcement learning is that the actual reward, in other words, completing the task, is often very far away from the seed, from the initialization by definition, even for humans, right? If you're supposed, between the point where you can juggle 4 eggs or 5 eggs without destroying them, and the starting point where you have no idea, that there's a big gap there. And even as a human, think about it. How are you going to learn this? How are you going to learn to ski down, Colbert Couloir in Jackson Hole? If you're a complete beginner skier, you might. I mean, how do you do that, right? So, what are the steps that you need to take to gradually learn the task and get to the actual reward? That the design of the reward function. So, what they do here in Eureka is, according to the paper, 3 contribution, achieves human level performance on reward design across different open source environments and benchmarks and so on and so forth. Solves text manipulation tasks that were previously not feasible by manual reward engineering, pen spinning in particular, and enables new gradient-free in-context learning approach to reinforcement learning from human feedback. So what they're saying is the following, like, even if you know what the end reward is, like, let's say pen spinning is the reward. You wanna teach the robot pen spinning, but you don't know how to design a reward function to do it. Like, you don't know how to teach the robot how to get there, because you just if this is the age-old problem of, Lionel Messi probably doesn't know how to teach people how to play soccer. Michael Jordan probably doesn't know how to teach. Some people are amazing teachers, but those are rare. The people who are really good at particularly low-level dexterous type functions, they are not very good at teaching people, and this is fundamentally what the problem is here. Okay, so they go further in the sort of the paper, which I find interesting, reward function design problem. The problem is, what is the actual problem? So the reward function is a function with 4 variables: M, R, P, and F. M is the world state. M itself is a function of state, action, and transformation function. Then we have R, which is the reward function. P is the policy, and F is the evaluation. I don't want to go into details here. This is not, the purpose of the Not Even Wrong podcast is to give people a sense of what it feels like to run a hedge fund. So I by no means want to compete with, say Yannick Kilcher or people like that who are actually discussing papers. First, because I'm not qualified to do that. I don't have a academic background in artificial intelligence, but more importantly, also, I just don't think it's necessary that another person discusses papers online. What I'm trying to do is give people a sense of what it feels like to run a hedge fund. So what my niche is here is, I'm trying to give people, particularly people who have a sort of inclination or desire to move into a direction where Orange Capital Partners is, which is the purpose of Orange Capital Partners is to generate wealth by investing in fundamentally new concepts and engineering practices. So how do you come across fundamentally new concepts and engineering practices? What does that even mean? Well, one way to do that is to understand science, to understand technology, and to find those transition points when science morphs into technology, and then technology morphs into a business, and then a business turns into a profitable business, and then the profitable business can scale, and there is this sort of, for lack of a better word, flywheel. I don't like it. It's an Amazon word, but it is what it is. It means something, right? It's or a positive virtuous circle. Those are the kinds of moments that we're looking for. And me going to Neurips, discussing papers like this, the purpose of these papers and the way I select the papers I discuss is really finding that trajectory, right? So if I was an AI, if I was a machine learning experiment, then my reward function would be, okay, find those trajectories that where potential rollouts are such that we have fundamentally new concepts in engineering practice. This would be the idea, and that's why I'm discussing this. And again, just for clarification, I am not here to discuss papers in detail or anything like that. So the next paper I want to discuss is the DPO paper. I think that was probably the biggest action that I saw. There were two papers that I saw lots of actions. One's a DPO paper, and the other was the train of thought actually, which I'm going to discuss in another episode. This one, direct preference optimization, the idea is the following, right? You have large language models and you have reinforcement learning with human feedback that fine-tunes the large language models, aligns them with human preferences for safety reasons, but also for just experience, right? You want to have a good experience. So write me a poem that sounds like Rilke in English with a little bit of a hip hop, whatever. How does the LLM know what that even means? Well, it learns by being fine-tuned. And the idea of the DPO paper is that you can parameterize a function from pairwise data. So from a data set, you can infer a function that then can be implemented in sort of a straight, parallelizable, faster computational way. Okay? So key to DPO is a data set, the availability of pairings, whatever it is, jokes, music, paintings, recipes, description of recipes. A is preferred to B, D is preferred to B, and so on and so forth. From that data set, a parameterized estimation function can be learned, which gives the best guess of what the distribution of output of a given prompt should be. So I'm sorry for the maybe a bit convoluted language here, but for anybody, for economists in the audience, think of transitivity on steroids, right? This is one of the fundamental concepts of economics is transitivity. If you like A better than B and you like B better than C, then you better like A better than C. This is what this is all about. There are some fundamental pairing classifiers from the 1950s. They talk about some models that were, again, they go back to the 1950s. The idea is, imagine you have a set of pairings, okay? I write a joke, and I write a joke, and I give you, write me a joke. I give you two versions, A/B testing. Think about that. This version of the joke and that version of the joke. I like this better. Okay. Now, this version of the joke or that version, I like this better. This version, so on and so forth. And what they found, what the authors of the DPO paper found, is a parameterized function that is learnable, that can take that data and implement a sort of implement the right prompt or the right answer to a prompt, to be precise, in a much faster way without. So you implement. You can have better answers to prompts without having to do the reinforcement learning. This is the key. The mathematics are quite involved. They go back to, like I said, to the 1950s, when preference estimation, preference pairing, decision making, this goes even further back to von Neumann and these people, maximum likelihood estimation. I mean, these concepts, I've encountered them in the 90s when I studied economics, and they're coming back. This is really, really important. The idea is always, the fundamental idea is really the same, right? You have a set of data, and now you're trying to estimate. You have a new input. You're using a set of data which is somehow related to the input, and with the training you design a function that can take the input and project some output that is useful. In the case of robotics, it's an action. In the case of classification, it's a classification. In the case of an LLM writing a poem, it's the thing can generate, a sequence of words that look like a poem. But the fundamental idea is, okay, we have a data set, and how can we learn from that data set to extrapolate an input that doesn't come from data set but has maybe similarities or maybe not, but let's say it's similar. Now, this brings me to the last paper, which is open data set, which is related. That's why I put it in this episode. It happens actually to be the paper that Yannick Kilker was involved, so shout out to Yannick. I think his work is exceptional and really interesting person in general. I think very good combination of academic and business and savviness, and then also human, just a nice human being, at least from what I can tell. So OpenAssistant conversations, what they did, I mean, he and many other people in that paper, it's think of it this way, like what I just spoke about in the DPO paper, right? The DPO paper lives and dies with the data sets. And what I would say the biggest advancements in AI at least in the next few years, will be in generating interesting data sets. We have the models, particularly the LLM, and we have the transformer architecture. We have all these tweaks now. We have diffusion models. We have state space models, or derivations of those, such as RNNs and DNNs. Those are the models. Those are think of it like the parameter space. But now we need to feed those models the data so the parameters can be tuned. And the data set, the data collection, the data generation will be key. There was a quote that I came across in the conference. It had something to do with Oscar Wilde. It said it's depressing how little useless information there is out there. Whatever, typical Oscar Wilde. But it's really interesting, right? There's very little useless information out there. You can use any kind of information. What Kirchner and et al. Did here is they collected conversations between LLMs and humans and annotations of those conversations. And why is this useful? Well, now you have a data set that tells you, well, with this prompt and this answer, this was preferred to that. A preferred to B, B preferred to C, C preferred to D, but D not preferred to F, so on and so forth. With that data set, you can then use DPO, or you can use other things. But the key is you can create a model you can train a model based on that data set to fine-tune your own language model. And you don't need, or you can use a language model, actually. You can use a language model out there and then fine-tune maybe that model for your purposes using that data set. They have thousands and thousands of conversations in different domains, different topics, probably about recipes and cooking and jokes and sports and business and law and whatnot. And this is just the beginning. I'm sure more can be done. Academia will do more. Maybe we need some sort of Manhattan Project where, like when I remember when I lived in Singapore in the 1990s, Singapore created a sort of a broadband initiative where the whole town was built on broadband. And I think something like that could happen now, where a country like Singapore or Switzerland or Estonia, those types of countries are typical for Finland. They decide we're just going to create this massive data set to solve X, whatever that may be. Engineering. Take engineering, yeah. Well, why not create a massive data set with engineering tasks, conversations between engineers and LLMs, and then train those models, fine-tune them so they can be used. So to summarize, 4 papers that I discussed in this is part 2 of the Neurips conversation or discussion. And the 4 papers that I discussed, one is using LLMs for traffic scenario planning. One is using LLMs for reward function design, DPO direct preference optimization, which is some sort of offline reinforcement learning for aligning LLMs with human preferences, and then finally OpenAssistant, an open source data set with conversations that can be used to align large language models better with human preferences. Thank you.